Hello everyone, welcome back, and we're going to continue on the topic of block and tackle. So we discussed the mechanical efficiency, and we'll continue on the topic. So let's look at some more calculations here. Let me try to erase these. Remember we talked about the power and how to calculate the power. So power was defined as the force multiplied by velocity, right? So if you're inputting some power to this fast line, right, through the engines that you have there, and that's how you raise or lower the weight of the stands, right? So how much power input are you imposing? So the power input is equal to the force on the fast line, right? Because that's the rope that you're basically pulling or trying to work with, and that's the rope that you're inserting force on or imposing force on, right? So the fast line force multiplied by the fast line velocity, right? That's the definition of power, force multiplied by velocity. Now, what is the output power? The output is the weight, right? The weight that is pulling upward is raising or is being lowered, right? So the output power is equal to the weight multiplied by the velocity of the traveling block, right? The whole system right here. So now, if we have a frictionless block and tackle, W was equal to N multiplied by FF, right? So I can write efficiency, right, of the system. Efficiency is PH over PI, right? The output power divided by the input power. Remember, we have that formula for efficiency previously, and that is equal to W multiplied by velocity of the block, right? W multiplied by velocity of the traveling block divided by force of the fast line multiplied by its velocity, right? Now, remember that equation we had for W. W was equal to N multiplied by FF for an ideal mechanical system, right? You can go back there, check, and also the one that I just erased, right? That was the equation. Now, also the velocity of the traveling block, we can find an equation for it, and that's the velocity of fast line divided by N, right? The velocity of this block is 1 over N, the number of lines that you have there, multiplied by the velocity of this fast line. So this fast line is moving much more than the whole system here. So if you pull this one for 2 meters and then you have 5 lines here, then these 5 lines will move by 2 divided by 5, right? Which means 0.4 meters. So if you pull this one by 4 meter, pull, this will raise by and then you have 5 lines, assume, right? 4 by 5, then 4 by 5 is 0.8, right, meter. So that's how this velocity is found, divided by FF, nu F, and then the efficiency is equal to 1, right? Because all these cancel out. So the efficiency of an ideal mechanical system, efficiency is different from mechanical advantage, remember. Efficiency is related to the non-ideality of the system. For example, you have friction, right? That reduces the efficiency of your system. Mechanical advantage, on the other hand, tells you how much less force you need to put to raise or lower a weight W, right? Look at the again here. So you put, for example, you apply 50 pounds, you raise 100 pounds. That's mechanical advantage of 2. Here we are talking about the efficiency and non-ideality of the system, right? So that's it. Now, if you have non-ideality in your system, you can define the efficiency the same way, but you can't just directly write W is equal to N multiplied by FF. You can just keep W as it is, because in the non-efficient system, and if you have friction, then W is not going to be equal to N multiplied by FF. This relation does not exist for non-ideal system. That's for ideal system, because there are friction in pulleys and things like that, right? So W multiplied by nu F over N divided by FF multiplied by nu F. By the way, all these equations are in the book. This is chapter 1. I guess we are at page 8-9 of the book. So please go ahead. The book is written very well. Read through it and let me know if you have questions. But anyway, so here we get W is equal W over FF multiplied by NN, right? And you can calculate the force on the fast line to be W over, just using the same equation, right? En. That's lowercase n. So that's the force applied to the fast line, the tension in the fast line, right? Now, what is the total force that being applied to the derrick? So here is, you have the derrick, right? All the force that are being applied to the derrick is the top part of this derrick, right? It's basically pulling down the derrick, right? So there is a fast line, which is this one. There is a deadline. Deadline is kind of attached, and it doesn't move at all. So that deadline, let me see if I can find it. Yeah, so this is the deadline, and it's attached, and it's not moving, and that's, we may use it if we need extra lines, or this is, you see, a storage lane, but it's usually anchored here, so it does not move, right? So there is a force by that line, right? There is a force by the fast line. Let me see where I am here, right? The fast line, the deadline, and also the weight. So the sum of these three forces that are being applied to the derrick is the total derrick load. Make sense? So now W is W, right? So W is W. The force by fast line we just calculated is W over its efficiency multiplied by N, and the force by the tension actually inside the deadline is equal to W over N. This is not moving, right? Since it's not moving, then there is no friction, right? And since there is no friction, there is no efficiency here. So it's just W over N. These two are very similar, except that this does not have the efficiency, right? So this equation is the total force applied to the derrick. Again, this is equation 1.8 in your book. Okay, 1.8b, right? You can simplify this equation, and the simplified equation, I'm trying to find the space here. So FD is equal to, just factor out W. You see W is all there. 1 plus 1 over En plus 1 over N, right? I guess. Yeah, multiplied by W. So that's the equation that is the total derrick load. Okay, so next we'll do an example, and we'll talk more about this derrick load, because this derrick load is being applied to 4 legs, right? So we need to calculate the force on each of those legs as well. And the reason that we do this, we wanna have a derrick that withstand all these forces, right? So you need to exactly calculate the forces that are being applied to each leg of the derrick, and you want to make sure it can withstand that force. Okay, see you in the next video.